Hello and welcome to my talk. My name is Anup Das and I'm an assistant professor in Drexel University. The title of my talk is Compiling Spiking Neural Networks to Neuromorphic Hardware. This work is done by my doctoral student Shihao Song. The other co-authors for this talk are Nagarajan Kandasamy and James Sackerford, and we are all part of the Drexel's Electrical and Computer Engineering Department. This work is sponsored by the National Science Foundation. We start with an executive summary of this work. So we made two key observations. First, compiling spiking neural networks on off-the-shelf neuromorphic hardware and guaranteeing performance is challenging. Second, Dataflow models allow predictable performance estimations on hardware with limited resources. Based on these two observations, we propose our idea, which is the compilation technique for SNNs on resource-constrained neuromorphic hardware, embedding Dataflow analysis. This idea generated three key contributions. First, a resource-aware SNN partitioning technique. Second, a data flow-based performance analysis technique. And third, a performance-aware runtime mapping technique. We evaluated the performance of our compiler with state-of-the-art machine learning applications and found that our compiler resulted in 78% higher performance over state-of-the-art practices. A quick summary of neuromorphic hardware. A neuromorphic hardware, like multiprocessor systems, is a tiled architecture where a tile consists of a crossbar, input and output buffers. Tiles are also interconnected using a shared interconnect. A crossbar can accommodate n input and n output neurons, where n could be 128, for example, in the Dynapse hardware. At the intersection of the horizontal and vertical wires of a crossbar are the synaptic elements, and non-volatile memory can be used to implement those synaptic elements. A crossbar can have a maximum of n presynaptic connections per neuron. A crossbar also has a fixed buffer size to store spikes before they are routed on the interconnect. From the chip perspective, a typical neuromorphic chip can have a limited number of tiles. In Dynapse, for example, there are only 4 tiles or 4 crossbars. Now, these resource limitations impact performance. So we evaluate one particular performance metric, which is the throughput. So we evaluate the throughput obtained on Dynapse with limited resources using one of the current practices, which is the spine map technique published in IEEE TVLSI 2019, against the throughput obtained with unlimited resources. That means unlimited number of crossbars in the hardware. We compare this throughput against the throughput obtained on Dynapse using our proposed compiler. So we see that the throughput on Dynapse using current practices is 64% lower than the throughput with unlimited resources. On the other hand, our compiler resulted in 78% higher throughput than this current practice. With this understanding, we now present the outline of today's talk. We will talk about the proposed approach and our three key contributions, which is the clustering technique, the data flow modeling technique, and the runtime mapping technique. And then we will present the evaluation and finally the conclusion. So our proposed approach is shown towards the bottom of the slide, out of which the colored boxes are the key contributions which are part of our compiler toolchain. Now the compiler can take two types of input. It can either take a trained artificial neural networks written in PyTorch or TensorFlow, or it can take a trained spiking neural networks written in PyCal. If it is an artificial neural network model, it has to be first converted into a spiking form using the N2D2 software and simulated using CalSim. If it is a spiking neural network, then it can be directly simulated in CalSim. The model training and SNN simulations are performed outside the compiler. So the compiler works in 4 key steps. It first performs clustering, then it represents the clustered graph into a data flow format. Third, it do performance analysis with resource constraints, and finally, it do the runtime mapping. And we will now start talking about these steps in more details. We'll start with the clustering approach. The clustering approach groups neurons and synapses to form clusters such that these clusters can be mapped in its entirety onto a crossbar. So we take the running example of Linet 5 convolution neural network, which is used in handwritten digit recognition applications, which is shown towards the top part of this slide. At the bottom plot, we show the example of clustering. So we take a simple feed-forward connections, let's say connection from neuron A to neuron B to neuron C. And the clustering techniques groups these neurons. And in this example, we illustrate two clusters. So cluster 1 groups neuron A and C, while cluster 2 groups neuron B. Now, based on how neurons are grouped into clusters, although there may not be any cycles in the neural network, but when the clusters are generated, there can exist some cycles, as can be seen from this example. So once the neurons are clustered using an algorithm, which is detailed in the paper, we form a clustered graph, which is shown towards the right side of the figure. Now, in the clustered representation, the nodes are the clusters, which we call actors, and the arcs are the intercluster communications. The number on the arc represents the number of spikes that are communicated from one actor to another in one iteration of the application. Now, a node or a link can also contain initial tokens, which represent spikes from the previous iterations of the application. So once the clustered graph is generated, we convert it into Dataflow representation. Now there are different Dataflow models available. We select one, which is the synchronous Dataflow graph. These are computation models used to represent the streaming applications, and it incorporates cyclic dependencies. This is very important for us because, as we mentioned, although there may not be any cyclic connections in the input neural network, but when clusters are generated, there can exist some cycles. Therefore, having the ability to analyze cyclic graphs is important in our case, and therefore SDF graphs are well suited for this purpose. So SDF graphs can be used to analyze a system in terms of key performance metrics such as throughput, execution time, and buffer requirements. So what we did is we developed a tool called SNN to SDF, which is Python based, which converts a clustered representation of a clustered SNN and convert it into the SDFG representation. And then we apply max plus algebra to analyze the performance. Now, this performance analysis is considering unlimited resources. So next, we discuss how these formulations can be extended to consider resource constraint. The first resource constraint that we have is the buffer requirement. Now, since the number of crossbars in a hardware are limited, it might so happen that more than one actor or clusters are mapped to the same hardware. However, they cannot be executed simultaneously. To avoid that, we create back edges between the cluster. So in this particular example, we have shown that actor 4 and actor 1 are both mapped to the same hardware tile. However, the buffer space is limited, and let's say the buffers can accommodate only 5 spikes at once. So what we did is we created this back edge such that when actor 4, let's say when it fires, it claims the 5 buffer space at the start of its execution and releases them only when the spikes are consumed. By consumption, it means that the spikes are communicated onto the interconnect. In this way, actor 4 and actor 1 cannot be executed simultaneously. That means the actors has to be executed one after another. Beyond that, what we did is we created 3 other techniques to analyze the performance of this SDF graph onto the hardware. So first thing we did is a tile allocation strategy. So we used a greedy strategy to allocate actors to tiles such that the balance on each tile is so that the load on each tile is balanced. Second, we used TDMA, which is time division multiple access, to allocate time slices to actors mapped to the same tile. And we apply max plus algebraic formulation of the previous slide to analyze the performance with hardware resource constraints now in place. But all these analyses are performed at design time. However, to use such analysis at runtime, what we did is we use self-time execution, and in self-time execution, the exact firing time of the different actors are discarded, retaining only the order in which the actors must be fired. This is called the static order schedule. So we discarded the timing information and retain only the static order schedule from design time. At a runtime, whenever the actors are ready, they are inserted into a ready list and only fired in the order maintaining the static order schedule from the design time. In this way, by maintaining the static order schedules, we guarantee that the performance obtained at runtime will be the same as that obtained at design time. Next, we discuss a strategy to map the SDF graphs at runtime onto the tiles. So at runtime, the resource allocations may change, or the resource availability may change over time. This is because, let's say, one application is running on the hardware, may finish execution, and the resources can now be distributed to other running applications to increase their performance. But every time the number of resources in the hardware changes, we need to construct the static order schedule from scratch, right? And this is very time consuming. So to address that, we propose a new approach for runtime compilation technique. So where we create a single tile static order schedule at design time and store this schedule. Now at runtime, depending on how the number of resources change in the hardware, we recreate the static order schedule from the single tile static order schedule of the design time. That means we can just recreate the schedule without having to construct it from scratch. And the next slide, this slide, try to show how such ordering can be created at runtime. So the single order static order schedule is shown at the top of this figure, and we show two examples where in the first example we show the availability of two tiles, whereas in the second example toward the right we show the availability of three tiles. Now in both cases, the static order schedules on the tile for the actors are constructed from the single tile static order schedule. And later on in the evaluation, we'll show how much performance improvement we obtain due to how much reduction in compilation time we obtain due to this technique. This brings us to the evaluation technique. So we evaluated 8 state-of-the-art machine learning applications. These are image smoothing, edge detect, MLP MNIST, heart rate estimation, heart rate classification, CNN MNIST, LeanET MNIST, and LeanET C4. These applications ranges from feed-forward neural networks to recurrent neural network, and also the last 4 being the convolution neural networks, whose architecture is shown towards the bottom of this table. The number of synapses and the neurons of each of the applications are mentioned in the table, as also the number of spikes that are generated in the application and the accuracy. So we compared 2 state-of-the-art approaches. The spine map, which is our prior technique, which appeared in TVLSA 2019, which tries to minimize the number of spikes on the interconnect. However, if more than one clusters are mapped to the same tile, the clusters are executed in a random order. We also compared our approach against PyCurl, which is the approach that is published in IJCNN 2020. And this technique balances the tiles, tile load, which means that the clusters are distributed evenly onto the different tiles. However, if more than one cluster are mapped to a tile, then the clusters are executed in a random order. And we compare them against ours, where we use SDF graph to analyze the exact order in which actors need to be fired on the tiles to guarantee a performance. So first we evaluate the throughput. So in this example, we show the throughput for spine map, PyCurl, and proposed, and we see that the throughput using the proposed approach is 78% higher than spine map and 28% higher than PyCurl. Next, we evaluate the compilation time. We show the compilation time breakdown into the binding time, that is the time to find a mapping of actors to the tiles, and the scheduling time, which is the time to find the static order schedule. We see that to construct the static order schedule, it takes over 75% of the total compilation time, which essentially justifies our single tile strategy that we proposed in this paper. In terms of resource utilization, we show the resource utilization in terms of the tile utilization, buffer utilization, the connection utilization, and the bandwidth utilization. We see that all the resources utilization are less than 100%. That means the compiler can fit all of these applications to the hardware without violating resource constraints. We also evaluate the performance scalability. That means what happens to the throughput as we increase the number of crossbars into the hardware. So we see that compared to 4 tiles, the throughput is 11% higher with 9 tiles and 15% higher with 16 tiles. Finally, we show the runtime performance, and we compare the compilation time at design time, where the schedules are constructed from scratch, against the compilation time at runtime, where we use the single tile static order schedule to derive the schedules at runtime. We see that our proposed single tile based scheme achieves 67.5% lower compilation time at runtime. With this, we come to the conclusion. We have made 2 observations in this work. First, compiling spiking neural networks on off-the-shelf neuromorphic hardware and guaranteeing performance is challenging. Second, Dataflow models allow predictable performance and estimations on hardware with limited resources. Based on these 2 observations, we present our key idea, which is a Dataflow-based analysis-based compilation technique for SNNs on resource-constrained neuromorphic hardware. The idea generated 3 key contributions: resource-aware SSN partitioning, Dataflow-based performance analysis, and performance-aware runtime mapping. We evaluate our performance with state-of-the-art machine learning applications and found that we can achieve 78% higher performance compared to state-of-the-art practices. And this brings to the conclusion of the talk. Thank you for your attention, and the compiler toolchain is released with the name DF Synthesizer and is available on GitHub. Thank you.